but you're quite honest with yourself and you've got an open mind.
Don't forget that you can just look into different things. Sometimes it leads to very, very great discoveries. I entered the field of mechanically interlocked molecules by chance.
So hello, Oleg, and welcome to PhD Hard Talk. Thank you so much for making time to speak to me. How are you today?
Good, thank you. How are you?
I think I'm all right. I'm excited to have a conversation with you. So in terms of your research, I believe you're looking at supramolecular chemistry. Is that correct?
Yes.
So
exactly.
in terms of that, could you explain to a person like me, what is it?
Okay, so supramolecular chemistry is a really, really broad field.
Okay.
So I would say it's more a branch of organic chemistry. So it deals with compounds which have carbon atoms. And supramolecular chemistry is a chemistry that deals with chemical systems where molecules interact between each other without any chemical reaction.
Oh, that sounds fascinating.
If we talk about, let's say, organic chemistry or organic synthesis, so when we perform some chemical reactions, normally we have, let's say, two molecules which react with each other, and then they form a chemical bond. So they form basically a new molecule. But when we talk about supramolecular chemistry, it's not about the formation of strong chemical bonds between separate molecules,
right.
But it's just about weak interactions between the molecules. So one prominent example would be a molecule of DNA. So I think everyone knows this fascinating helical structure.
Yeah.
So DNA has two strands, so which are, wrapped around each other. And so these two strands of DNA, they are bound together due to supramolecular interactions. So these are weak interactions, and they keep two strands together. So this is one of the examples of supramolecular chemistry.
Okay, so in terms of what you're currently researching, in terms of your PhD?
So yes, broadly speaking, I work in the field of supramolecular chemistry, but another field of my research is so-called dynamic covalent chemistry to create supramolecular structures, namely so-called mechanically interlocked molecules.
Right, so if you're creating these things, how do they benefit a person like me?
Well, maybe first I show what mechanically interlocked molecules are, so that everyone have some idea what this means.
Right.
So there are two very popular examples of mechanically interlocked molecules. So one example is rotaxane. So when we have a ring, so a molecule which has this shape,
right,
and then we have another molecule which has a dumbbell shape, so like this. When we combine, so when we thread the ring onto the dumbbell, we get this kind of structure. So the two big, these yellow balls, they are too big to allow the ring to slip from the thread.
Right.
So this whole thing is one molecule, and it's called the rotaxane. So two parts, so the ring and the thread are bound, are held together, not because of some, not just because of some chemical interactions or supramolecular interactions, but also due to the topology. So because you cannot just separate the ring from the dumbbell without breaking one of the parts, without just tearing apart the ring or the dumbbell. So, and another example is a catenane. So catenane, so when we take two rings and then in a magical way we combine them and we get this kind of topology. So two rings connected with each other, not by any chemical bond, but just by topology. So again, we can, so this is one molecule and it has completely different properties from two rings separately.
So I'm trying to understand, we've got the catenane and we've got the, forgive me if I don't pronounce this right, rotaxane. What is the ultimate goal? Can we use this in food? Can we use it in infrastructure? What are the added benefits of playing with these molecules?
So these molecules were proposed initially to be a component for so-called nano devices.
Okay.
So very, very tiny devices where some motion can be performed. So let's say in the rotaxane we have the ring, and the ring can change the position. So basically it can move, and we can chemists can program the movement of the ring along the axle of the dumbbell. Also for the catenane, so we have two rings, and they can basically rotate in different ways, also in a controlled ways. And we can use these molecules to build nano-sized objects which can perform tasks on the nanoscale. So basically, it's something reminiscent of biological molecular machinery. So in biology, cells have different components, like some proteins, which perform tasks. So these are called molecular motors. So here, this is a minimalistic and artificial system created by humans, which has the ultimate goal to mimic the biological machinery.
Okay, so that I understand what you've just said. So if I'm sick, we can potentially create something that can assist me to detect an illness, or it can aid me with something that I'm missing potentially in my body. Is that what you're saying?
Yeah, so there are different applications proposed for these kinds of molecules, and also for so-called nanomedicine. So you can introduce these molecules to living cells, also in animals or in humans, and then program some particular task which will be accomplished or performed inside the cells. So this is one of the applications. Or it's also for some electronic devices. So to, I don't know, to change the electric current by some stimuli, or whatever. So I would say that so this is a really fundamental topic, and ordinary people will probably never see that this exists, you know.
Yeah.
But maybe in the future, so when they take some medicine or when they use some electronic device, or I don't know, maybe there will be some so-called chemical computers developed in the future. So they will just use it, but these molecules will be part of those things.
Okay, so now I'm thinking about wars. I mean, there's a race to create the strongest or the most powerful weapon, in a sense, globally, as we know. So can this be used to create a weapon of mass destruction in any way, form, or shape, or it might just go in way out?
This is no, I doubt it. No, these are very innocent molecules.
Innocent.
Yeah,
I like that. No, I mean, thank you very much for sharing that. So in terms of I mean, we've touched on how this does benefit the community in terms of it can be used for phones, it can be used for, well, you didn't say laptops, but I'm just making it up, but it has the ability to make our lives much easier if it is used in the correct way. Is that correct?
Yes, exactly. Yes. So so again, I will repeat that this is fundamental research, and probably it will see some real world applications only in, I don't know, 30 years or 50 years. So yeah.
So basically, you're still at infancy in terms of this research currently, is what you're saying?
Yes, yes. I have to add that this topic, so topic of mechanically interlocked molecules, was recognized by a Nobel Prize in 2016, so quite recently. And this topic actually appeared only at the end of 20th century. So it's less than 30 years old, actually.
Oh, wow.
So it's just, it's starting to develop, and there are already multiple examples in literature how these molecules can be used. But yeah, there is still a long way to see this in the real world.
Okay, so let me ask you this: what interested you to go into this field?
Honestly, so when I started my PhD, I had a completely different topic. So it was about some molecular receptors, about dynamic covalent chemistry. So we were just developing new reactions, so new kinds of reactions, which we can use for some purposes. And this was basically serendipity. So the reaction. So again, so my research was about this mechanically interlocked molecules, and my particular project during my PhD dealt with the synthesis of these molecules. So I found a new way to create them, but that was not an intention of so when I started my PhD. So this is very interesting, because when you enter research as a PhD student, you can start something, so you can start one project, but if you're really you're exploring different things and you're trying stuff, and then one day you realize that this is something that I want to try, maybe it works, so it looks pretty interesting, and then you try and then it works, and then you say, oh, okay, so I want to investigate this, so I want to look into this, and you just start pursuing this direction, and then eventually you end up with the whole big project. And this project becomes the main project of your PhD.
Yeah.
So sometimes it's like that. Sometimes, of course, you have some projects from the start, which you choose.
Yeah.
And then you just pursue this project till the end of your PhD. You get some results and you publish them. But sometimes it's different. So sometimes something unexpected happens. And this is what happened to me. So I entered the field of mechanically interlocked molecules by chance. So I didn't plan that.
Well, congratulations, because it sounds interesting to me, and especially if it's still in its infancy, I feel like there's a lot of opportunity to grow. And hopefully 20 years time, you'd be the one to say, I did discover this and I've published 10 journals and this is what I've done, and you're standing there and we're all clapping. So brilliant in terms of that. So in terms of advice, what advice would you give somebody that's looking at something that's quite niche and there isn't that much research in the field? What advice would you give them?
Many things depend on the supervisor. And in my case, I was really lucky to have a great supervisor who encouraged students to make their own discoveries. So of course, every student has a project, and they start working on them. but he always supports students to look for some really cool stuff which can, appear out of nowhere during your regular research. Of course, I would recommend to pursue something that really grabs your interest, that you don't just blindly follow your own project, but you don't forget that you can just, look into different things, or within your project, you should notice something that is unusual, and then try to investigate this. So, and then sometimes it leads to very, very great discoveries.
And sometimes it doesn't. We have to
sometimes yes, but it's hard to tell if it works or not. But I think people should try that. Yeah. Because the greatest discoveries normally are made in this way. So when you don't expect something, or it just it's a serendipity, and then you just need to notice it. Yeah. And then pursue this. But of course, if you just work in your narrow direction and you don't want to notice anything around, of course you will get eventually your project done, but maybe you're missing out something really, really exciting.
I'm agreeing with you. I think the biggest example, I think, is anidin, in terms of how it was done. It was a PhD student, I believe, who came up with the tablet itself, and it was just a moment of negligence that he went away and forgot to check the samples, and came back and he discovered, oh, I've come up with something, it's brilliant. So I totally agree with you in that instance. I guess in terms of where do you see yourself in 5 years' time?
It's a very hard question. So my answer is that I cannot predict for sure. So I'm finishing my PhD in roughly half a year, so pretty soon. So of course, this question, so whether I should go to industry or academia, is like really important question nowadays for me. My first priority would be academia, but unfortunately, usually people cannot tell for sure if they will stay in academia or not.
That's true.
So I would like to, because I like freedom, I like, that when people have space for creativity, so when I have this space, and I think that science and academic research is really great opportunity for that. But academia nowadays is really, really competitive, and so many things now depend on how good your publications are. It depends on your previous supervisors. It depends on your connections with other people from your field in academia. So it's really, really complicated, and I'm trying now to keep my mind really open. Yeah. So not to get super depressed after I realize that I cannot stay in academia. So I believe that I can find also really cool positions in industry. So also probably connected to research. But let's see. So in my ideal world, in 5 years, I would finish postdocs, and I would just get a permanent position at some university, and will start my own research group, and will pursue the things I'm really passionate about.
Okay, so I mean, it's great how you've explained, because you've put things into perspective to say there is a lot of competition to remain in academia, because there's a lot of people with PhDs currently, or maybe previously as well. I haven't done the research, but you're quite honest with yourself and you've got an open mind. I guess that's what the viewers will enjoy, is the fact that, you know, it's not just you that's going through it. There's someone else sat there at home thinking, I don't know what to do, and they're working themselves up and they think about the Viva. You know, there's so much that's going on. So thank you so much for sharing that, because it will help maybe one person or maybe 10, we don't know. But, you know, it's brilliant that you've opened up and shared that, because I've had interactions with individuals who are really affected by the fact that, you know, if they stay in academia, for example, they think there's a lot of red tape, so they can't perform to the best of their ability. If they go into industry, it's not really their passion, but they have a bit of freedom. Let's say, for example, those who've done biomedical sciences, etc., there's a lot of labs, you know, and they're like, I will drop down a level. I'm not ready to drop down a level because I've worked really, really hard. So, you know, it's brilliant the way you put things, because I think it will help all those individuals who are still trying to find themselves and what the best decision could be if they were to step out and take a limb in terms of industry.
Yeah,
so in terms of your Viva then, are you excited?
Actually, I haven't started to write my thesis. So it's still relatively, I mean, it's not a long way to go, but it's still lots of things to be done. So yeah, I don't have this feeling that it's really close. So I think I will have it maybe in 4 months. So when it's 2 months before my PhD defense, then I will start, you know, I will get the feeling and maybe get a bit nervous. But right now I'm still really focused on my current projects, because I have to finish them very soon. So yeah, I'm not thinking about the defense.
Yeah, I guess it's different, you know, because I do qualitative research. So obviously we work on our work in terms of the language or the discourse structure. We've already done our literature review and all that stuff. So it's quite strange to hear that, you know, you've worked with the molecules, but now you need to start, you know, the writing side. We write before we can go out there, or whether we're using case studies to then look at the data or discuss what we've discovered based on the literature review that we've done. So it's quite exciting to hear that you do it vice versa.
I also do lots of writing. So we during our research we publish papers, and yeah, basically we first do some experiments, and then we sit and write, and then we publish, and then we do experiments again. So it's very mixed. Yeah. So for me, writing my PhD thesis will be just, you know, summarizing stuff. So just taking, collecting everything together. I plan to write a cumulative thesis, which means I will just use the papers I already published. So I will combine them, and I will write an introduction part, which is, I don't know, maybe 30, 40 pages.
Right.
And that's it. So this will be the thesis.
Oh, amazing. So in terms of your work, what you've published, if anybody wants to read more, where can they find it?
Yeah, I mean, I can just leave my the links to those papers. I think that some chemists might be interested in that, but I don't think that it's really for broad audience.
Yeah. I mean, you won't find me reading it because I wouldn't understand. But from the presentation today, I think I understand, you know, the balancing scales. But for me to then describe what you said, maybe it might prove difficult for me personally. But I don't know for everybody out there. But I'm sure there's someone out there who's thinking of what you're doing and they would want to read. So definitely, if you share
absolutely,
the link,
I think we can just, I can leave the link somewhere, you know, below the video.
Brilliant. Thank you so much for your time today, and I wish you the best in terms of your finals and also your publications in the future and near future.
Thank you.